Hello, and welcome to the notes on operating systems. So hopefully you've had a chance to do the reading and watch the videos, and then these notes are going to be useful because they'll give you an idea of what you're actually going to be held accountable for. The book does go into some more detail than we're necessarily going to have to worry about on certain things. So again, hopefully you did that reading. It was chapter 10. And then let's see what we've actually got to talk about today. All right, software categories. You should be aware of the difference between application software, programs that help users solve real-world problems, and system software, programs that help manage a computer system and interact with the hardware, etc., etc. So, examples of application software. You know, it's the stuff that you're using on sort of a daily basis. So you could think of this as things like, Microsoft Word. You could think of it as any games you play. You could think about it as like a calculator program. That sort of stuff. All right. Versus the system software, programs that help manage a computer system and interact with the hardware. It also includes tools and environment for creating applications. So Jess is a tool or an environment that we use to create software. All right, so Jess would count as system software. Obviously, the big one would be your operating system. All right, so for a Microsoft or a PC, you're looking at Windows. For Apple, I think Apple usually goes. Don't they have like Snow Leopard or whatever? I don't have an Apple, but I think they usually go through Cats. Maybe they're on. I think they're on Tiger King at this point now. Does that sound right? Like Tiger King, is that the Apple operating system? I'm not really sure. Again, I'm more of a PC person. But things like that. Antivirus software you could consider system software. So if you have like antivirus or something like that. That's help managing the computer system, so you could consider that system software. So again, just kind of know the difference between those two terms. All right, next, the roles of an operating system. So an operating system is system software that provides an interface through which humans can interact with the computer. All right, so examples might be the login. You've got your login here. You've got your desktop. You've got your file explorer. All right. All of these things allow us to interact with and use the computer. All right. And it also manages computer resources such as memory and input-output devices. The OS makes sure that all running programs nicely share the computer hardware. And for us, what we're specifically going to look at is we're going to look at how memory and the CPU are shared. So again, remember, this is not an operating systems course. We're just kind of give you a high-level sort of view of a lot of different topics. So we're going to give you a high-level view of sort of the types of things an operating system does. If you go and take a full operating systems course, it's going to go into a lot more detail. You're going to go into a lot more specifics. This, again, is really just more of a general sort of overview so you can have some basic background knowledge about operating systems. Okay, so when you have your computer, usually you have several programs that are running at the same time. All right, so here we just have like a silly little example, but here's a clock. Here's a internet speed test. Here's a Netflix movie. And here's Microsoft Word. All right, so we've got all of these things that are running at the same time. And it's not just computers, like on a phone too. You can have, as I'm sure you're all aware, You can have lots of apps running all at the same time. But to execute a program, it first needs to be loaded from the hard drive into main memory, and then it needs to use the CPU. So each individual program needs access to the CPU, but we've got this situation where you've got multiple programs running at the same time. So the question is, how does that really work? How is the memory shared? How is the CPU shared? So that we can create this impression of multiple programs running at the same time, even if in reality it's just a single program running at any given instant. All right, so that's kind of what we're going to look at a little bit here. All right, so memory management. All right, multi-programming, the technique of keeping multiple executing programs in main memory at the same time. And then memory management, the process of keeping track of what programs are in memory and where in memory they reside. All right, and again, we're going to look at two different topics in here, single contiguous and partition memory management. The book goes into paging, and paging is the way is pretty much how modern operating systems are going to handle things. But again, in this course, we're kind of keeping things simpler, so we're just going to focus on these two. But there's lots of resources out there if you want to read more or research more about paging techniques. Okay. All right. So let's start with single contiguous memory management. All right. So single contiguous memory management. Not really something that you're going to see these days, but it starts as a nice kind of conceptual framework. So the idea is at most two programs are in the memory, the OS and a user application. So at any given point in your main memory, you've only got two things running. You've got the operating system and you've got a single application program. So what is an advantage of this? It's fast and easy to implement. All right, so it's pretty good pro. The con should be pretty obvious. You can only run one application at a time. All right, so, I mean, obviously, this isn't a technique that's used in modern operating systems, but it's going to give us sort of a framework to talk about issues that all operating systems and all memory management techniques have to consider. So again, not totally relevant to today's computer systems, but it still creates problems and situations that we have to deal with in today's system. So it kind of starts, it's a good place to start our discussion. All right, so what is the issue that comes up with memory management? The main thing that we're going to talk about here is called address binding, which is converting logical to physical addresses. All right, so when you write a program and you create variables and you do all that you do in the program, we have to come up with like addresses. And we saw this when we were writing assembly, load 4, add 5, out 5, etc., etc. You can think of those as like not actual addresses, but logical addresses. All right, and what I mean by that is a logical address is defined relative to the start of the program, i.e. it assumes that the program starts at 0. All right, so if the program starts at 0, we're saying load in the 4th thing, or load in, or add the 5th thing, or output the 5th thing, or whatever. Whereas a physical address is the actual location in memory. So what we can do is we can convert these by saying, all right, the physical address, once we load this into memory, if we take the starting address of the program in memory and add that to the logical address, we can get the actual physical address that we need to run the program. So, for example, here's your program. It's saying load 4, load 5, out 5. All right, so we take this program, we get it from secondary storage, we load it into our main memory so that we can actually run the program. It gets loaded into the main memory here at 10984. That's the physical address that it's being loaded into. All right, what we can do and what address binding is all about is we can say, all right, take this load 4, and now we know that this load 4 actually means load 10988. And this add 5 really means 10989. And this output 5 really means 10989. So again, if this is where our program starts, in memory, these numbers become our offsets from that starting location, and that way we write the program with these relative references. It can be loaded into memory at any spot or any address, and the program will still run correctly because it's being used from these relative locations, and you've got these offsets that are saying, all right, if it's loaded in here, this means go here. If it's loaded in over here instead, this means go there, and it doesn't matter where it's loaded in, the program is still going to execute correctly because you have these offsets. And this idea of address binding is going to be true whether we're talking about, whoops, not the sheet that I wanted. It's going to be true whether we're talking about single contiguous memory management, where we have to do offsetting of addresses. It's going to be true if we're doing dynamic partitioning. It's going to be true if you're doing the more involved paging technique. But it's this idea of taking your program, which has these relative references, and then converting those into physical addresses on main memory so that it can be loaded in at any point and still work correctly. All right, so again, that's kind of why we're bringing up single contiguous right now, is that the issues it presents are the issues that show up no matter kind of what language we're looking at. All right, so let's move on now to partition memory management. All right, so partition memory management. OS and any number of executing programs are in memory at one time. And then two schemes for dividing up memory among the executing programs are fixed partitions. All right, so we'll start with fixed partitions. But now we've got this idea that we've got main memory, and we can have multiple programs in at once. So we're not just saying that you get the operating system in one program. We're now saying you're getting the operating system and multiple programs. So one way of setting up these partitions is called fixed partitions. And what this implies is that you have a fixed number of partitions, each with a fixed size. Now, they don't all have to be the same size, but their size is kind of set ahead of time. They have a fixed size. So a fixed number of partitions with a fixed size, and then each partition is either empty or is occupied by a single program. All right. So you've got all these slots in memory. The slots can be different sizes, but those sizes are fixed. Like this slot is always 2 gigabytes. This slot is always 6 gigabytes. This slot is always 6 gigabytes. Those sizes are fixed. And then programs can be loaded into those slots. And maybe they take up the whole slot, maybe they don't, but those slots are fixed. All right, so again, if we're taking just a closer look at what we have here, all right, so this memory below has 4 partitions. Of sizes 2, 2, 6, and 6. Now, technically it has 5, but I'm not counting the operating system right now because that's always occupying that first partition. I mean, the operating system can never not be involved. So it's not like we can ever really load a different program into there. So I'm just considering it these 4 that we have right here. Now, based on the picture that we have right now, 3 of them are empty. So A is actually a program that's executing, but 3 of them are empty. Now, let's say over here it says we want to add new program B of size 3 gigabytes. All right, so with a fixed system, all right, we're going to put B inside of this slot. All right, we can't put it here because this slot is only 2 gigabytes and program B requires 3 gigabytes. But because the partitions are fixed, we're kind of wasting a lot of space here because this was a 6 gigabyte partition. B only needs 3 of it. So we're wasting 3 gigabytes of space here. So B is getting the entire partition even though it only needs half. So I think it should go without saying that this is pretty wasteful. All right, this is not an ideal situation when you're talking about memory management. All right, so the question is, if it's so wasteful, what's our alternative? All right, so that brings us to something called dynamic partitions. So instead of using fixed partitions, we can use dynamic partitions, and then hopefully we're not going to have quite as much waste. All right, so the idea behind dynamic partitions is that programs are allocated a contiguous programs are allocated a contiguous chunk of memory that is exactly the size needed. All right, so if we look at our situation here again, instead of breaking these up into fixed sizes, we've just saying, all right, we've got 5 gigabytes of space here, we've got 8 gigabytes of space here, A, for whatever reason, happens to be right here. All right, so when we decide to add program B of size 3 gigabytes, we could go over here and say, all right, let's load B right here, and this is where B will go. And that will use up 3 gigabytes, which now means we'll have an empty 2 gigabytes right here that something else can be loaded into, because this is going to go from 2 to 5 gigabytes. All right, and then over here we have an empty 8 gigabytes where things can be loaded in. All right, so we're still putting it all together. Like all of program B is going in one contiguous spot. All of program A is going in one contiguous spot, and that's kind of the big idea with partitions, is that you're loading the programs in as one contiguous thing, versus paging, which if you read about in the book, is you're kind of breaking it up into different pieces. But with partitions, it's one contiguous thing, so you always have to make sure you have like enough space for it. So obviously this is a lot way better than what we had before because we're not wasting space, but it is going to put more responsibility and more processing on the operating system, because the operating system needs a policy to decide where new programs are placed in memory. Questions? No? No questions? You sure? All right. I mean, feel free to ask a question if you have one. All right. Welcome back. So, we just saw that dynamic memory allocation, we don't have to waste big, large, empty spaces. But the question is, how are we actually going to manage this? How are we going to dynamically allocate our memory here and come up with a technique that's going to, work? So we've got 3 choices that we're going to go through. One is called first fit, one is called best fit, and one is called worst fit. You're probably saying to yourself right now, why would we ever use worst fit? Well, let's just say you've got a nice little surprise coming in store. All right, so first fit would be you select the first empty partition big enough to hold the program. All right, so that's first fit. Best fit would be you're selecting the smallest empty partition partition. What's awkward about having a spelling mistake on here is then it will be up on the internet for people to see forever and ever and ever and ever. All right, so select the smallest empty partition that is big enough. And you might be able to guess at this point, but worst fit is going to be select the largest empty partition. And I could say that is big enough, but that's kind of assumed, because if you don't have a partition that's big enough to hold it, then you're not actually going to be loading the program with this memory management technique that we're talking about. In actuality, there are ways around that, but for our purposes, if you don't have a spot big enough, you're not actually loading the program. All right, so it says, can you give a rationale for each? This is where I would pause and we would have a discussion and we would go back and forth and there'd be this great trading of ideas. But that's a little hard to do over a YouTube video. So possible rationales, something like first fit. It's easy to implement. Probably pretty fast. There's not a whole lot you have to figure out. You just say like, all right, this is big enough, let's put it in here. This is big enough, let's put it in here. Oh, this one's too small, let's move to the next one. Oh, let's put it in there. All right, so pretty easy to implement. All right, best fit little more work's going to go into this one, because if you're going to select the smallest empty partition that is big enough, you do have to know the sizes of all the partitions, and then you have to figure out which ones are big enough and which ones are not big enough and which one is the closest. But on the upside, it seems, and I'm going to write the word seems here, it seems like it might be the best use of space. All right, like why bother using something that's twice as big as it needs to be? All right, it's like the old joke. Is the glass half empty? Is the glass half full? Or more accurately, is the glass twice as big as it needs to be? So again, we're going to see that there's actually some issues here, but for right now, we'll just go with seems. And then worst fit, all right, possible rationale is if you're selecting the largest empty partition, what it's going to end up doing, let me slide this, is it's going to leave bigger chunks of memory that maybe something else can be loaded into, rather than tiny little slices that may not be big enough to really be useful. So if you're doing best fit and you've only ever got a little bit left over, it might be that that little bit left over is totally going to waste because no program is so small that we can fit it in there, or it's half the size of most of our programs, or so on and so forth. So worst fit leaves bigger chunks, which might actually be more useful for us when we're actually trying to run our programs. All right, so let's run through a couple of examples where we look at how each of these would actually perform. All right, so we'll start with first fit because I said that one seemed to be the simplest and the easiest. All right, so here is our main memory, our hypothetical main memory. A and B are already in there. All right, and we want to load program C, program D, program E, and program F. So first fit says that you take the first available spot that's large enough. So we want to load program C. So program C takes up 5 gigabytes. We're looking for the first available spot. Well, this spot right now from 2 to 9 gigabytes is 7 gigabytes long. So that means it does have room for C. So we could put C in here. All right, C starts at 2. It ends at 7 gigabytes, which then means we have this new 2 gigabyte space that we've just created. All right, so program C has been loaded in. We're good to go. All right, next we go to program D. All right, program D is 5 gigabytes, same size as program C. We go along here. We say, all right, here's an empty spot, but it's only 2 gigabytes, so we don't actually have enough room. We go, oh, A is already here. We get to this next empty spot and say, all right, finally here we have enough space to load program D. So we're going to go here. We're going to load program D. And again, if the empty space started at 12 and program D was 5 gigabytes, that's going to bring us to 17 gigabytes right here. All right, and now program D is in memory. All right, so now we're at program E, which is 9 gigabytes. So we go along. It's obviously not going to fit here. We get to here. This is from 17 to 27, which is 10 gigabytes. So that will be long enough. So we can put program E right in this spot. And it will go from 17 to 26 gigabytes. And now we're going to have this 1 gigabyte space left over here that maybe something can fit in, maybe something can't. All right, but we've got the first 3 in. And then we get to program F, which is 7 gigabytes. Again, it's not going to fit here. It's not going to fit here, but it will fit in this spot here at the end. So we can say, all right, program F is 7 gigabytes. Let's put it in here. Here's our program F. All right, this empty space started at 28. Program F was 7 gigabytes, so that brings us to 35 gigabytes. And then we're left with empty space here. We're left with empty space here. And we're left with empty space here if there are other future programs that we want to load. All right, so we end up with 2 gigabytes right in here that could still be used by something. We only end up with 1 gigabyte right here that could be used by something. And we end up with another 2 gigabytes right here that could be used by something. And again, remember, in our system here, the program can't be divided up. The program has to be loaded in as one contiguous piece of information. All right, so that would be first fit. All right, so now let's go on to best fit. All right, so pretty much same situation, same memory setup, only now we're going to use the best fit, which again is you want to use the smallest possible space that you can use. All right, so we're loading program C at the start. We have at the start this space right here, which is 15 gigabytes. We have this space right here, which is 9 gigabytes. And we have this space right here, which is 7 gigabytes. All right. So since this is 5 gigabytes, we want to use the smallest spot that's still going to hold it, which would be this first one that started off at 7 gigabytes. So C is pretty much going to go in the same place it did the first time. All right, so there's C, and again, it's going from 2 to 7. All right. So next, we have program D, which is 5 gigabytes. So it's not going to fit there, so that's out of the question. This, again, is 15 gigabytes of space. This one is only 9 gigabytes of space. So instead of putting it here like we did for first fit, we're going to put it over here because that's the smallest available spot that will still fit it. All right, so we're going to put D here. All right, so there's our D. Again, it's 5 gigabytes, so that goes from 28 to 33. And that's going to leave us with 4 gigabytes of space over on this side. But we do have the first 2 in. All right, we're already seeing that they've ended up in different spots, but we have the first 2 in. All right, now we get to program E, which is 9 gigabytes. All right, so it's not going to fit here. There's only 2 here. It's not going to fit here. There's only 4 here. So this is the smallest possible space that will still actually fit it. So E is going to go right here. It's going to take up 9 gigabytes of space, which will bring us from 12 to 21 gigabytes. And we're good there. And now if we look at program F, which is 7 gigabytes, we can see that, all right, we have 2 here. It's not going to fit. We have 6 here. It's not going to fit. We have 4 here. So if we look at this one's only 2 gigabytes of space now. This one's only 6 gigabytes of space now. And this one is 4 gigabytes of space. We've got a problem, all right, because this requires 7 gigabytes of space, and like I just said, in our system, we can't divide it up, so there's actually no room for this program. All right, we can't run it until space frees up. All right, so best fit, you're probably like, oh, clearly best fit is the best choice. It actually creates this situation where you end up with lots of little slices of memory, none of which may actually be big enough to hold the program that you want to run. All right, so let's take a look at the worst fit situation. All right, so worst fit algorithm. Again, it's counterintuitive, but it's actually going to work out pretty well. So in this case, what we're doing is we're taking and putting something in the largest possible partition that we can find. All right, so we've got program C. It's the first one. It's 5 gigabytes large. All right, in the first two algorithms, we put it here because this was the first space that it would fit. In this algorithm, we're going to do something totally different. We're finding the biggest space. So again, this one's space right now is 7 gigabytes. This one's 15 gigabytes. This one's 9 gigabytes. So C is actually going to get placed right in here at the start. All right, so we're going to put C right in here. It's going to use up 5 gigabytes, so we're going to go from 12 to 17. All right, but notice I still have this big space of 10 gigabytes left over here. All right, so program D is 5 gigabytes. Again, this is 7. 17 to 27 is 10. 28 to 37 is 9. So this is still the largest spot I have in memory. So D will get put right next to C. And that will go from 17 to 22 gigabytes. All right, so now I've got 7 here, I've got 5 here, and I've got 9 here. All right, so program E is now, so I've done this one, I've done this one. Program E is 9 gigabytes. All right, so again, it won't fit here, it won't fit here, but it will use the entirety of this right here. All right, it's going to use all 9 gigabytes of the space that's left over there. All right, so it'll take up that entire spot. And then last but not least, we have program F, which is 7 gigabytes. And we can take a look at what we have left over. We've got 7 gigabytes here. We've got 5 gigabytes here. This one's not large enough, so, and there's nothing left over here. So F is going to go in right here. It's going to use up all of that space. And notice they all fit, so that's good. And not only do they all fit, but more importantly, look at the empty space that we have. All right, it's not split up between lots of little chunks. We still have one large chunk of 5 gigabytes left over. Now you might be saying, yeah, but you picked the numbers to make it work out this well. Yes, but it holds true regardless. Worst fit is creating these larger chunks of memory that are going to be more useful to you because they have more space to actually run things in them. So that's kind of this whole idea behind like dynamic partitions and dynamic memory management and things like that. For this class, this is what you need to be aware of. Now, again, in your reading, you did see and it did cover paging techniques. We're not going to worry about it in here, but the premise behind paging is more or less that not only are you breaking up the memory, but you're now also breaking up the program. And the program doesn't necessarily have to take up one contiguous spot of memory. And actually, the entire program doesn't even need to be in memory all at once. All right, you can just bring part of the program into memory and kind of trade it in and trade it out instead of having everything in at once. So again, this system that we've kind of talked about, it's useful because it gets you thinking about how memory works, how you have to use logical versus physical addresses, and kind of how that address binding system works. But more modern systems are not necessarily doing it this way. They're using the paging technique that your textbook covered, where the program is getting divided up, the memory is getting divided up. You can trade things in and out. And yes, there's like a more complex addressing scheme of address binding, but it follows sort of the same principle of these more simple systems. All right. So again, this sort of gives you the conceptual framework to think about this sort of stuff, even if it's not necessarily how the computer sitting in front of you right now is managing its memory and kind of handling things. All right. So we're going to stop here for right now. There's going to be some practice problems for you to try out. And then next class, I mean, whatever class even means these days, we'll talk about like the CPU scheduling side of it. So this was sort of the memory side of it. Next time we'll talk about the CPU scheduling side of it and how the programs trade off and share time using the actual processor in the computer. Okay, welcome back to the operating system notes. What we looked at last time was a lot about memory allocation and sort of the different ways we could do that. We looked at best fit, worst fit, first fit, just to kind of see the different kind of trade-offs between sort of each sort of allocation technique. So the switch today is, instead of looking at the memory side of the computer, we're going to look at sort of the processing side of a computer. So you've got different programs that you're trying to run on the computer. When those instructions are actually being executed, you need to take advantage of the CPU. I mean, the CPU is what's actually sort of executing those instructions as, you know, the electrical signals flow through the gates and everything else that we've learned about. So how does the operating system kind of share that resource between lots of different programs that might all want to be running at the same time? All right, because even though it seems like they're running at the same time, it's really just one program that has the control of the CPU in any given moment. All right, so first slide here. Process management. A process is a program in some stage of execution. So it's run, the user's opened up the program, they're doing something in the program, it's in some stage of execution. Using multiprogramming, a computer system has many active processes, each at various stages of execution. They take turns sharing the CPU. All right. So process management is tracking the progress of the processes and managing the sharing of the CPU. And that's sort of our big topic for today, is how do we share the CPU among different processes that need to run at any given moment. All right, so let's start by taking a look at something called the process life cycle. And we'll kind of explain what each of these boxes mean and then how you would travel from one to another. All right, so a new process, you can think about this as when a user starts a program. All right, could also say opens a program, but we'll just stick with user starts a program. All right, so a user starts a program, and then once everything is loaded into memory, we get kind of into this ready state where it's ready to have its turn sort of with the CPU to sort of do everything that it needs to do. And technically the CPU needs to be employed to like get everything it needs, but long story short, new we can just think of as a user starts a program. All right. Then it moves into this ready zone, and then when it's ready, it can either go over here to running, which means the process is picked to use the CPU. All right. It can terminate, which means the process terminates execution or ends execution, which basically means it's done. It's done everything it needs to do. It's been closed. The person's not using it anymore. Now, when it's running, All right, sometimes the CPU needs to be taken away for something else. So the CPU can be taken away from the process. All right. Now, when you're running a program, all right, the program will do what it needs to do, but then occasionally it needs to stop and sort of wait, either for a response from the internet, a response from the user, or something else. So sometimes processes end this waiting cycle where they don't really need the CPU, they're just waiting for something to happen. So this arrow represents sort of the process needs to wait for input output data from the web etc. All right, so it can be in sort of this waiting phase. It can come out of the waiting phase, which is when the process gets what it was waiting for. So the input might be provided, the data may have come across, so now the program is again ready, but it may not actually have control of the CPU at any one point. Is that everything? Couple other things. Running just means that it's on the CPU, so it's using the CPU right there. And just sort of a reminder that only one process is running at any time. All right, so as you're using a computer, you can kind of float between these different processes, these different boxes where you're either starting a program, the program is ready to be executed, but it might not have control of the CPU. It's currently running. Sometimes it gets taken away before it finishes. Sometimes it finishes and becomes terminated. Sometimes it has to wait for user data. And then once it gets that data, it might not instantly run again. It might have to go to this ready situation where it's kind of waiting its turn for the CPU. So these two, they're both sort of like the process is waiting, but in this box, it's usually waiting for like user input or data from the internet or something like this, where in the ready box, you can kind of think of that as waiting for the CPU. So both boxes represent this situation where it's waiting, but one is waiting for the CPU and one is waiting for sort of user input or something else. So the question is, when we have lots of processes in this zone, how do we pick which one actually gets control at any given moment? All right. So that's what we call, or making that decision is CPU scheduling. So it's the act of determining which process in the ready state should be moved to the running state to take a turn using the CPU. Many processes may be in the ready state at the same time, but only one process can be at the running state at any one time. So which one gets to move from ready to running? And this is basically the decision of the OS. This is where the OS comes into play. Decision is made by the OS. This is why the operating system gets paid the big bucks. It has to make important decisions like who actually gets to use the processor at any given moment. All right. So let's take a look at some different algorithms the operating system could use to figure out who actually gets to use the CPU. All right. So 3 that we're going to look at in this class. First come, first served. So the process uses the CPU in the order which they arrive to the ready state. So whoever shows up first gets to use the CPU first. Whoever shows up last gets to use the CPU last. You can basically think about this like the processes just get in a line, and you move through the line, and whoever's at the front of the line gets to go first. Whoever's at the end of the line gets to go last. All right, shortest job next. The ready process with the shortest estimated running time uses the CPU next. All right, so if you've got a job that's not going to take very long, the idea here is let's just get it out of the way. Let's get the shortest jobs done first so that we're not sitting there waiting for really long jobs to be finished when we could get this short job done right away. It's like when you're a good person at the grocery store and you have like 50 items in your cart and there's somebody behind you that's just like buying a pack of gum. It's a nice thing to let that person just check out with their pack of gum before you check out with your 50 items in your grocery cart. All right, so if you're not a person that does that, you should be. And that's the idea behind shortest job next, is if somebody's only got one or two things that they need to do really quickly, just let them go ahead so they don't have to sit there and wait for your big, long job to finish. And then last but not least is round robin, where each process runs for a specified time slice and moves from the running state to the ready state to await its next turn if not finished. So basically, trying to be as fair as possible, you come up with a set time slice. Everybody gets that amount of time. If they finish before that time is up, great. If they don't, they then have to wait until their turn comes back around. All right, so instead of letting anybody just finish while everybody else waits, everybody gets a set amount of time. They use their time. If they finish, great. If they don't, then it just keeps going around until it comes back to being their turn, and then they get it for another, set amount of time, and it just keeps going around and around and around in a circle until everybody eventually is able to complete their process. All right, so those are the three we're going to look at, and same thing with like the memory allocation. We're going to just kind of break it down in more detail so you can actually see how each of those would play out with an example. All right, so we'll start with first come, first served. All right, so we have 5 processes here, P1 through P5. All right, you can think of those as basically 5 different programs that are running. They each have a service time, 140, 75, 320, 280, 125. All right, now to make the math easier, we're going to assume that these all sort of showed up at the same time. Not totally realistic, but we're just going to kind of assume that all 5 of these showed up at the same time, but they did show up in this order. So even though they all showed up at the same time, technically P1 was first, P2 was second, P3 was third, P4 was fourth, and P5 was fifth. All right, so let me just put that little note here. Again, not necessarily totally realistic, but it's going to make our job easier. We're just going to say they all enter the ready state at roughly the same time. All right, and then these numbers here are the amount of time the CPU, amount of time the process needs the CPU. All right, so what we're going to do is we're going to make something called a Gantt chart. And this is going to kind of let us see sort of the overall efficiency of this method. All right, and the Gantt chart is just going to kind of lay things out and just basically give us like a time scale of sort of what's happening. All right, so at time 0, process 1 is going to start running. All right, so here we've got process 1, call this P1. And because this is a first come, first serve algorithm, it gets the processor or the CPU until it finishes, which is going to be at 140, all right, because it uses it until it's done. After P1 finishes, then P2 is going to get to run. Now, P2 is only 75, but don't forget, they all showed up at the same time, so P2 really had to sit there and wait for 140, and then only at only once P1 finished could P2 start using the CPU, so it finishes at 215. So even though it only needed 75, it actually ended up taking 215 to finish. Now, the same thing is going to be true as we go down here. So P3 takes 320 for our little time unit here, but it had to sit there and wait 215. So that means from start to finish, P3 actually took 535 of our time units here. All right. And then we can keep going here. So P4 again needed 280, but it had to sit and wait 535, which actually brings us all the way up to 815. All right. And then same thing with P5. It only needed 125, but it had to sit and wait for 815. So that brings us all the way down here to 940. All right, and this right here is our Gantt chart. All right, so that's what, if you're asked to make one, this is the sort of thing that I'm looking for. And then what we kind of want to know with these different algorithms is like how good of a job are they doing? So the way we're going to measure that is average turnaround time. All right, now turnaround time is the amount of time between when a process arrives in the ready state the first time and when it exits the ready state for the last time. So again, in our little example here, everything entered the ready state at the same time. So that's going to make our job a little bit easier. So if we're looking at the average time, all right, the first one took 140. Now, even though the second one only needed the processor for 75, it actually took 215 for it to finish. The next one actually took 535 to finish. The next one actually took 815 to finish. And the next one actually took 940 to finish. So when we take all of those, we divide by 5. All right. I'll give you a second to do that in your head. All right. I assume you all have an answer now. It should be about 529. All right. So that's sort of our first algorithm. All right. First come, first serve. And you can sort of see the problem here is that some processes can sit there and just wait a really long time before they get to use the CPU. And you've got something like process 5 there that only needed 125 of our time units, and it ended up taking 940 to actually get it to completion. All right, so there's first come, first serve. All right, let's take a look at shortest job next. All right. All right, so we're using pretty much the same, we are using the same exact numbers, but we're just going to see what difference this results in when we actually do it. All right, so shortest job next would mean that if they all arrived at roughly the same time, we would start with process 2. All right, because that is the shortest job. So 0 to 75. All right, once this one is done, our next shortest one would be P5. All right, which was 125. Now it still had to wait, like we didn't get rid of the waiting part, so it still had to wait, and that would bring us to 200. But then this one is done. All right, next that would bring us to P1. All right, and P1 still had to wait, so it's actually over at 340. All right, and then P4 would be next, because we're always picking the next shortest job. 340 plus 280 should be 620. And then last but not least, the longest one, P3, would go at 320. Whoops, it takes 320, which actually means it would be at 940. Sorry about that. because it had to wait 620 first. All right, so again, if we try to calculate the average turnaround time, right, it's not just the individual service times, it's that plus how long they had to wait. So in our case, it would be 75 plus 200 plus 340 plus 620 plus 940, all divided by 5. Again, let me give you a second to do that in your head. All right, I assume you've added all the numbers up at this point. Okay, good. And now you've divided by 5. All right, perfect. And you should end up somewhere around this. All right. So we can see that the order in which we process them is going to make a difference. All right. We've got 529 for this first one. We've got 435 from the second one. And all we did was like change the order in which we ran the processes. Now, hopefully you're going to see, or hopefully you can kind of intuit that this is a little harder because you might not necessarily know how long the process is actually going to need the CPU for. You might have an estimate, but now you have to be keeping track of how long you think each of them is going to use the CPU for. You have to find a way to organize them. There's a lot more overhead that's going to be involved in trying to do a shortest job next than there is going to be in a first come, first serve. Now, maybe that overhead is worth it. Maybe it's not. You know, it depends how accurately you can actually estimate some of these times here. So let's take a look at our round robin algorithm here. So general idea is the amount of time a process is allowed to use the CPU before being preempted, which is basically a fancy way of saying interrupted, and return to the ready state to allow another process its turn at the CPU. So what is the average turnaround time using round robin? Assume the time slice is 50. So in this situation, processes don't necessarily get to run to completion. All right, they get 50 units. Once they use their 50 units, they have to give up and let the next process have its turn, and they keep going around in a circle like that. All right, so when we draw our Gantt chart, this one's going to unfortunately be a lot more involved. All right, so we start with process S1 again. So there's process 1, all right, and it gets from 0 to 50, but since it needs 140, it's not actually done yet. But that doesn't matter because now P2 gets a turn, and P2 goes from 50 to 100. Again, P2 needs 75. It only got 50. It's not, in fact, done yet. All right, so then P3 gets a turn, and then P4 gets a turn, and then P5 gets a turn. And at this point, we're up to 250. Everybody has had an equal turn. So now we go back around. All right, so now P1 would get its second turn at the CPU. All right, and that would bring us up to 300. Now notice P1 in total has had the CPU for 100, but it needs 140. So it's still not done yet. And I don't know, I don't remember if I pointed this out. This is a problem with doing videos. But we did say up in the problem that each one gets it for 50. So I didn't just pull that number out of my head. That's what we specified at the start of the problem. All right, so now it's going to be P2's turn. Now, if you notice, P2 only needs 75. It already used 50. So if it doesn't need the whole time slice, it just doesn't use it. All right, so here's P2. It's not going to go to 350. It's going to go to 325. And I'm going to put this up top so that we know this is where the process actually finished. All right, so P2 is done. We don't have to worry about that one anymore. And then we can go on to P3. All right, so P3 gets it for 50 seconds or 50 units or whatever it is. And then that brings us to 375. and then it's P4's turn again. That brings us to 425. And then it's P5's, and you can see why I said this one's going to be a little more annoying. This is going to bring us to 475. And now, again, P5 is close, but it's not quite done yet. All right, we've given it to it for 100 units, but it still needs 25 more. So it's going to have to wait again for its next shot. Now, we are on our third time with P1. P1 has already had it for 100 units. It takes 140, so that means it's not going to need its entire slice at this point, right? It's going to finish during this turn that it has. It's going to use 40 of its intervals, which is going to bring us to 515. And again, I'm going to put that up top so that we know this is where one of them is actually finishing. All right, then we'll put the check mark up here to show that we're done with P1 and P2. Now it's going to be P3's turn. All right, this is P3's third shot at it. So again, P3 is one of our longest ones, so it's not going to be finished yet. But that brings us up to 565. And then it's going to be P4's turn. All right, and that's going to bring us up to 615. All right, and then we're to P5, which again only needed 125. It's already had it for 100, so that means it is going to finish this time around. All right, it only needs 25 of what it has, so that's going to bring us up to 640, I believe. All right, and then P5 is done. Now, again, we don't have to give it back to P1, we don't have to give it back to P2, because those have already finished, so we go straight to P3. All right, and that's going to bring us to 690. And then we're going to go to P4. That's going to bring us to 740. All right. P5 is done, P1 is done, P2 is done, so now we're right back to P3. And you can see that we're just going to alternate back and forth between these two for a little bit. All right, that's going to bring us to 790. And then we've got another P4, and that's going to bring us to 840. How many P4s have we had so far? 1, 2, 3, 4, 5. So it has it for 250, so P4 is going to be finishing the next time around. All right, so we'll have our P3 here at 890. We'll have our P4 here. And again, it's only going to need 30 of the time that it has. So that's going to put us up at 920 here. All right. And then let's see, what are we at for our P5s? We've had 1, 2, 3, whoops, not P5s. P3s. 1, 2, 3, 4, 5, 6, which means it's already got 300. So it also only needs it one more time. All right, so we'll do a P5 here. All right, it only needs 20 of it. So that's going to bring us to, why did I say P5? I keep doing that. All right, P3, sorry. All right, that's a P3 right there. And that's going to bring us to 940. All right. All right, so a lot more involved here, but you can kind of see sort of the principle here. Each person gets the same amount of time. Each process gets the same amount of time. And we kind of just share the CPU in equal increments. So here we have P2's finish time. Here we have P1's finish time. Here we have P5's finish time. Here we have P4's finish time. And here we have P3's finish time. All right, so again, if we were going to do sort of the average time, All right, we would say 325 plus 515 plus 640 plus 920 plus 940. Divide all that by 5. And we get to 668. And you're probably saying to yourself, all right, why did we even bother to do all of that work? First come, first serve gave us 529. Shortest job next gave us 435. This gave us 668. You're telling me we did the most work for the worst result. Yes and no. You have to remember that these are just the random numbers that we picked. All right, it isn't necessarily always going to work out that way. Plus, there are a lot of other advantages to this round robin technique because processes aren't just sitting there and waiting for something else to finish. The time is shared so that each one sort of gets to use it equally. And in fact, the round robin is the one that is used most often. So even though in our little example here, it looks like it's the worst, there's lots of other reasons that actually make this sort of the dominant choice when we're looking at scheduling algorithms. All right. So let's take another look at some stuff here. So first things first, what is different about the round robin is that things don't always come to completion. So let's just talk about this just to make sure we're clear. Preemptive scheduling, all right, is a scheduling policy in which the OS may take the CPU away from a running process before it is done using it, so before the process is finished. Are these scheduling algorithms preemptive or non-preemptive? Explain. So hopefully after just going through those, it should be clear that this is non-preemptive. The process is allowed to finish before the next one starts. Shortest job next is also non-preemptive. The job is allowed to finish before the next one starts. The only one, in fact, that we just covered that's preemptive is the round robin. We saw when we went through that it would go back and forth between the different processes. And what we're going to talk about now is that creates a whole bunch of not problems, but issues that you have to consider and manage if you're going to switch from one job to the next and trade off who's controlling the CPU. All right. So let's talk about process management and the process control block. So the process control block is used by the OS to store information about processes that are not currently using the CPU. The PCB includes current values of all CPU registers for the process, including the program counter, general purpose registers like R and the CCR bits, and accounting information. So why do we think the OS needs to store all of these register values? All right, especially when we're doing some sort of preemptive process. All right, so I'll give you a second to think about it. No, that's a good idea. Oh, no, I didn't think, but that would make sense. Anybody else? All right, so generally, the idea here is that if the CPU has the process taken away from it, right, it needs to pick up where it left off. When it regains control of the process, it kind of needs to know, where was I? What was I just working on? Where's my head at? So this process control block basically allows us to do that. So for processes that have the CPU taken away, from them, which again is what we're calling preemptive. All right, you need these values so that their execution can resume exactly where it left off the next time it gets to run on the CPU. All right, so basically, if you're going to take away the CPU, you need to put it exactly the way you found it when the process comes back. All right, so it's like, I don't care if you make a mess, just make sure everything's back to the way I like it when I come back. All right, that's basically the idea here. Doesn't matter what the other processes do. They can go crazy. They can change registers. They can change CCRs. They can throw a party, whatever they want to do, as long as you put it exactly back the way it was when the original process comes back and needs the CPU again. In that way, it doesn't care what was running on the CPU 2 seconds before, as long as it returns to its state that it had when it left. All right, and again, just kind of this idea of, whoops, wrong sheet. You know, the reason this is necessary is there's only one CPU and therefore only one set of CPU registers which contain the values for the currently executing process. So each time a new process is moved to the running state, register values for the current running process are copied into its PCB so that it knows exactly how it was set up. Register values of the new process moving into the running state are copied from its PCB into the CPU so that it can pick up wherever it left off. And then this exchange of register information is called a context switch. All right, so that each process can kind of always pick up right where it left off, and it doesn't matter that, you know, it took 20 different turns to actually finish it. It always picked up right where it left off and could just kind of continue on with whatever it was doing. All right, so that kind of wraps up the notes on operating systems. So I hope this was helpful. I hope that the reading was helpful. I hope those videos were helpful. Obviously, if you have any questions, just reach out. The next step is that we're going to be doing a lab that involves some Python programming and involves some OS type stuff. Now, normally you would do the OS stuff on an applet, but that's going to be a little tricky, getting the applet on everybody's computer. So what I'm probably going to do is I'm actually going to film a video of going through the applet, and you're just going to have to get the answers from the video. All right, so again, I hope this was helpful. Let me know if you have any questions, and best of luck.